Students, we are going to continue our discussions on mechanical behavior in lecture number 18. So, in the last lecture, we started this new topic. What is that? That's on mechanical properties of nanomaterials. Remember, in our syllabus, we are supposed to discuss various properties of nanomaterials and how these properties are affected by the size of nanomaterials, shape of nanomaterials. So, to give you some recap of the last lecture, we discussed about some basic aspects of mechanical behavior, right? Mostly on tensile test. How tensile test is to be conducted, what are the different sample specifications, and the different other techniques which can augment the tensile test, like hardness test. At the end, I showed you some things about some aspects about defects in the materials, because deformation, majorly by plastic deformation in these cases, occurs due to generation and movement of the defects in the material. And defects can be different types. We have discussed that. Mostly we discussed about the line defect, that's on the dislocation. So, what all things we discussed about mechanical properties? The few things which are important, okay? Like stress-strain relationships, that's very important. Hardness provides basic mechanical properties. But we didn't discuss about what the effect of temperature, fluid properties. We have discussed a little bit about the viscoelastic behavior, because these are the things which may be important. The fluid properties and the effect of temperature on mechanical properties will not be very important in case of mechanical properties of nanomaterials. So, we have not discussed about that. Well, and mechanical properties means the material's behavior when it is subjected to some kind of mechanical stress. Okay. Well, we always put it mechanical stress because it can be other types of stresses also, thermal stresses. So, properties like elastic modulus, ductility, hardness, and the various types of strengths as well as ductility are important for the mechanical properties. And this is very important for designer, because strength is very important for designer, but other things are also important for many other aspects. By designer we mean mechanical engineers or the civil engineers, okay, who normally uses the material for their own basic purposes. So, as far as test and relationship is concerned, you need to know different types of stresses: tensile, compressive, shear. And of these, tensile is the most important thing. Why? Because this provides the stretching of materials. If you pull the material, if you pull this thing up, how the material will behave, that's what is dictated by the tensile. Compression means, if you think of a pillar in a building, and building is very tall, then the pillar is subject to compressive stress. That is kind of a stress things which are like this. That's compressive stress. Okay. This is the tensile, and this is the compressive. By arrow, I mean the direction of loading. Okay. So, this is a sample, you are pulling it up, and this is your sample. If this is a sample, then you are pushing it to the sides. That's compressive. So, in the building, if you have a pillar or a beam, that's normally subjected to the compressive. Shear is what? When you have material like this and you are applying such a kind of stress, that's called shear. Stress strain curves are actually provides you the basic relationships when this kind of loadings are applied. Out of these three different loading, as I discussed, tensile is the most important one, because most of the materials fail by the tensile loading. We rarely find failure by compressive, rarely you will find. It happens, but very rare. but comparatively when you pull a material, material breaks apart. That's why the tensile is the most important way of thinking. In tensile test, we use a specific sample with a particular cross section and a length, and then pull it apart by force F and measure the elongation or the reduction of the area as well as the force per unit area, which is nothing but stress. So how do you do that? That's how it happens. You have a sample of specified length L0, you pull it apart using a force, the length increases, and initially the deformation will be uniform. Remember, by deformation we are talking about a plastic deformation, not elastic. Okay, that's what is our basic objective. We are nowhere bothered about the elastic deformation here. We are mostly bothered about plastic deformation. So at the beginning, I know in case of 3, the deformation is uniform all throughout the sample. But after a critical load, the deformation will be concentrated in the specified region of the sample, that's called neck. And this neck is where the deformation is concentrated. Okay, and then after some, then all the subsequent deformation will be only taking place in the neck region. Finally, the neck will grow and it will break apart. Okay, so now we can measure various properties, length and these other things also, right? And by doing different calculations, so this is the force divided by the area. That's nothing but F by A0. That is how engineering stress is defined. Engineering strain is defined by delta L by L0, where L0 is the initial length and delta L is the increase of length, right? And then we can have a stress strain plot, which is nothing but initially of elastic part followed by plastic part, and the demarcation is given by the yield strength. And then finally, you have a maximum load at which you have a ultimate tensile strength, and after that the load decreases and material fractures. Load actually does not decrease. This is reflection of necking actually. And we will not discuss much about details of that. So there are 2 regions, elastic and the plastic part. And we are most interested in the plastic part. The elastic part is governed by Hooke's law, but the plastic part is governed by defect generation and movement, right? Well, that's the maximum tensile strength, that is maximum load by the initial area. Ductility is always measured by change of length divided by the original length, and change of length is elongation. So delta L by L 0, that is what is the ductility, right? We also define as true stress. True stress is defined as a load divided by the instantaneous area. As you know, area is keep on changing as the material length increases, right? That's obvious, because length is increasing means area has to decrease, volume is constant. That's why as you increase the length, area must decrease. So therefore, in order to reflect the change in area, we need to consider a different type of definition of stress, that is called true stress. True stress is defined as F by A. F is the force, is the actual area resisting the load. Similarly, you can define 2 strain also, which is nothing but delta L by L integrated over L0 to L, and that's nothing but a log of L by L0, right? And this is how defined, this is how the instantaneous elongation per unit length divided by the actual length is integrated. Okay, so if you integrate this one, you get that equation. So that's why it's log of L by L0. And 2 stress, 2 strain curve will not show any kind of a thing like a effect of necking on the curve that keeps on increases. You can see that, and that's because you have taken care of that by using the instantaneous area. Flow curve. Flow curve is what? Flow curve is nothing but the curve which will depict the behavior in the plastic part, and that equation is equal to sigma equal to K epsilon to the power n, where sigma is this 2 stress, epsilon is 2 strain, K is a constant known as a strength coefficient, n is the strain hardening coefficient. And if you take a log on the both sides, you can measure the slope. Slope will provide you the value n. N is the strain hardening coefficient. Okay, you can always use hardness as one of the ways to measure the material's mechanical properties, because in many cases you may not have the facilities to measure the tensile strength, and you may not have the sample also to prepare a particular geometry of sample. So in that case, its hardness is the only way to measure the mechanical properties. Okay, this indicates resistance to wear, plastic deformation, even scratching. You know the Mohr scale, right? That's where actually scratching can be used to measure hardness. In the Mohr scale, diamond has the highest hardness, talc has the lowest hardness. In between, you have 10 different materials present. So polymers actually show viscoelastic behavior compared to the metals. In metals, if you apply a load, deform it, then keep it for some time, and if you remove the load, material will come back to original shape and the size immediately. If it's deformed in a plastic elastic regime, okay. But if it is viscoelastic deformation, if you increase this strain, then keep it for some time, and then you decrease the load, it will not come back to the original shape and size immediately. It will never come back. It will take some time to come back to original shape and size, and that's because of the viscoelastic behavior. Viscosity of the material in the polymer material is so high, the chains which are deformed elastically, it takes some time for them to come back, and that's why actually you need to know these aspects very well. So this is a unique behavior in the polymers. Then we will discuss about something about the point defects. Defects can be point defects. Point defects can be vacancy or interstitial, or maybe substitution solid atoms, or maybe self-interstitial. In case of normal metallic materials, in case of ceramic or the kind of ionic material, you can have Frenkel or Schottky defects. All of you have probably read about it. Okay, there are different types of voids, like octahedral, tetrahedral voids. They actually are also point defects. Then most important defects are the line defect, which we discussed a lot. They behave like a caterpillar moving from one end to the other end, and dislocations do move like that way. So dislocations can be edge or screw. Edge dislocation is nothing but extra half plane, and that's basically depicted by this kind of symbol, where this is the slip plane and that is the dislocation line. Okay, so they are perpendicular to each other. In a screw, this is parallel. The slip plane and the screw, the direction of the dislocation line, they are parallel to each other. That's the difference. Screw looks like atomic element in the screw dislocation looks like a screw from the top and bottom if you look at it. That's why it's called screw dislocations. So once you move a dislocation from one end of the crystal to the other crystal, it creates a shape, or there's a sleep. Okay, and this dislocation movement is characterized by Berger vector. All of you know that in every crystalline structure there is a specific Berger vector. Dislocation in the material looks like this. This is on the left side, this is titanium, on the right side is silicon, and dislocation looks like a line sequence, or they may look like a curved one. Dislocation in ceramics, they also look like this alumina and tantalum and titanium carbide, they look like also line. So they also deform by plastic deformation. Well, dislocation generated from these sources like fang reed sources, or maybe from the gain boundaries, and they move. When they move, they keep this minimum distance from each other so that they don't overlap the field associated with themselves. In FCC, dislocation plane is 111 and direction is 110. So when the dislocations actually move from one side of the grain to the other side of the grain, they come in front of an gain boundary, and gain boundaries can act as an obstacle for the movement of dislocations. And because of that, dislocations can get piled up in at the gain boundaries. So in a multicrystalline material, like in a large number of grains, then these effects is very significant. Okay, so gain boundary can act as an obstacle. That's what it leads to gain boundary strengthening, and also the Hall-Petch relationship, which we are going to discuss today. So as you know, this is the two gains you can see there. So this is the normal way of showing that. Dislocation generated from one gain boundary moves and reaches the other gain boundary. Now those two grains may not be on the coplanar, that is the slip plane for this grain and this grain may not be on the same plane. So therefore, even if dislocations want to move from this grain to this grain, it cannot move because these planes are not continuous. That's why they are two separate grains, right? Not only that, even if they want to start the dislocation process on this grain, the force required for that process may be different on this grain than this grain. So therefore, this means that gain boundaries can act as an obstacle for dislocation motion, and that's why they can provide strength, because any kind of obstacle to the path of dislocation motion is going to make the material stronger, right? Because dislocation needs to cross over that obstacle, or dislocation needs to break that obstacle. That's what it is. All of you know the hurdle race, okay? And in a hurdle race, the runner moves from one hurdle to other hurdle, right? That's why they can cross the hurdles. Similarly here, the dislocations are facing a hurdle, big hurdle at the grain boundaries, okay? This is a kind of a big hurdle, right? HURDLE. This hurdle needs to be crossed over. So they can actually force this dislocation generation movement in the other grain, or they can actually cross over this grain boundary. But the second one is difficult. First one is easier, okay? Nonetheless, whatever it is, they need to put a lot of force on this boundary. That's why they can actually allow the grain boundary or the dislocation to move from one grain to other grain. So such a kind of things leads to pile up a dislocation in the grain, right? In this grain, grain 1. And this pile up leads to stress built up on the grain boundary, correct? This is nothing like people standing in a railway ticket counter, as you have seen probably, no? So they are pile up. Many passengers are buying the tickets, so there's a pile up created at the front of the ticket counter. And then if the first person, which is the front person, a person standing at the front, if that person is moving a little bit, so the line will move on the backward directions. That is what is known as a back stress, right? That means the first person is a little bit pushing the back, that gives a back stress to the person behind him. And same thing gets percolated down to the end person, right? Since the person standing at the end of the cube. The same thing will happen here also. So dislocations getting piled up in the grain will apply stress on the grain boundary. So only when this stress will reach a critical value, the dislocation will, this dislocation movement will start on the other grain. A generation of dislocation movement will start in the other grain. As you know, grain boundaries actually, in a multicrystalline material or a bulk nanostructured material, you have large number of grain boundaries present. So therefore, this aspect is augmented. This aspect is felt the large number of grains actually. Every grain boundary will act as an obstacle, and this will lead to huge strengthening effect. You will be surprised to note, if I have a copper with a grain size of 10 micron and grain size of 15 nanometers, the strength or yield strength of that copper will be almost 4 times. Okay, that's what it is. So grain boundaries can act as an obstacle to the dislocation motion, and that provides the strengthening effect to the material. That's something which you need to understand very well. So I'll go back here. Okay, that's mainly because of these aspects. Grain boundaries provides obstacle to the movement of the dislocations. Remember, plasticity or the plastic deformation is dictated by the movement of the defects. Generation and movement of the defects. The more is the movement of the defects, more is the slip steps created at the surface. The more is the plastic deformation. So if grain boundaries are not allowing the dislocation to move, material will not deform. So material will show strength higher and higher. Okay, that's something which is very unique because of the grain boundaries. Well, this is shown here also in a atomistic structure. Dislocation starting from this grain, will slowly move to the other grain and then get stopped because of the grain boundary. Well, this aspect was first conceived by Hall-Petch, right? You should know that Hall-Petch, they first time discussed about these aspects. Okay, that's something which you should know very well. So what they told is very simple, very, very simple aspects. So if you have grains like this, right, these are the grains. As you see, this is the dislocation pile up at the boundary. Okay. Let me put the color different. So, this is suppose boundary on which the pile up is happening. Okay. And you can always draw another grain here. Correct. That is how it looks like. These are the several grains. Now, as I said, the pile up which is happening at the boundaries, once it reaches a critical value f star, let us suppose the critical value is f star. Critical value means critical value of stress, of shear stress. Once it reaches this value, the dislocation motion in this grain, this is grain 1, this is grain 2, in this motion will start. That is what we discussed. So, now suppose number of dislocation present in this grain 1, G1, the number of dislocation is n, right. So, as you know, if the Berger factor is B, then this is what is total displacement. Each dislocation leads to displacement by one Berger vector, right. In FCC crystal it is A by 2, 110, where A is the lattice parameter. So, if each one is giving such amount of displacement, n number of dislocation will give you n into B amount of displacement, and that if you multiply with the shear modulus, it gives you the modulus versus distance, gives you this the stress per unit length, right. Stress per unit length is Newton per meter, not Newton per meter square. Stress per unit length. Remember, modulus B is in terms of nanometers. Okay. So, that is the unit of meter, and modulus is always Newton per meter square. So, therefore, the multiplication of these two will provide you force per unit length, and this must be equal to the shear stress which is required tau minus tau 0 into 1 minus nu is the Poisson ratio multiplied by the pi L, where L is the length of pile up. What is the pi L thing? You know, in a circle, if L is the radius, the pi L gives you half of the circumference, correct. And if L is the diameter, then what happens? Pi L gives you the total circumference. Same thing here, correct. If we know the grain size to be given by L, okay, then that is what it is. Pi into L is the periphery of the grain. That is something related to the grain size actually, correct. As the grain size decreases, pi into L also decreases. So, then what is tau minus tau 0? Let us explain. Tau 0 is the value of the shear stress which is used for other strengthening mechanisms. There will be other strengthening mechanisms, like there will be solution strengthening, there will be British precipitation strengthening, there will be dispersion strengthening, many other things are there, correct. Or there will be strengthening because of aspects of Suzuki locking, many other things are there. So, those things if you take out from the total shear stress, that gives you the shear stress which is operating because of what? Because of the dislocation pile up. So, that tells you the shear stress for this dislocation pile up only, okay, which you are discussing. And remember, this is happening in grain 1, right, that is why. And this 1 minus nu is because of Poisson ratio, mu is a Poisson ratio, okay. When do you multiply 1 minus nu? Whenever Poisson ratio comes when you have a lateral and the longitudinal strain, that ratio is given as the Poisson ratio. And so, therefore, that gives you the 3D picture of the deformation. So that is what it is. So these NBG must be equal to tau minus tau 0 multiplied by 1 minus nu pi L, right. So mu is this thing. Now, as I said, tau 0 is the shear stress or contribution of the all strengthening mechanism except this gain boundary. So therefore, tau minus tau 0 gives you the gain boundary strengthening, where tau is the total strengthening, correct. And you know, shear stress tau caused by any tensile compression stress, shear stress tau caused by any tensile compression stress, that can happen because of compression tensile is given by sigma by 2. Okay, this is standard solid mechanics, all of you have read about it. So therefore, I can write down tau minus tau 0 is sigma minus sigma 0 by 2, right, very easily. Am I clear? And also you know that shear modulus G can be related to elastic modulus by 8 in a metallic material. Okay, it is all given, it is not G by 8, 3 by 8, okay, that we know. So therefore, we can write down N is equal to what? This is tau sigma minus sigma 0 by 2 multiplied by 1 minus mu multiplied by pi L divided by B 3 E 8, right. And we can always write down, correct, we can always write down one thing very clearly. What is that? The very easily we can write down this one, that is equal to C, a constant multiplied by sigma minus sigma 0 into D, I will come back to you what is that, multiplied by E into B. What is D? Well, so C is equal to, as you know, what? 4, 1 minus mu pi, correct, 3, that is it. Not only that, L and D are related, so that is it actually, because L and D is the grain size, okay. You can always talk about grain size for D like that. Am I clear? That is the grain size. So that is equal to N. N is the number of dislocation. That is proportional to this shear stress or tensile or compressive stress, grain size. Obviously, grain size increases, the number of dislocation will increase because you have much longer length, and also inversely proportional to elastic modulus and the Berger vector. That is very clear, right? Now we can expand that thing, okay. Now very simply, as you know, as the gain boundaries are acting as an obstacle, so dislocation load motions are heavily affected by the gain boundaries. The obstacle strength, the obstacle is defined by the obstacle strength, right. So obstacle strength we have defined as a F star, that is the critical value of shear stress which is required to be applied to start the dislocation activity in the grain 2. That is what is we have defined as the obstacle strength. Now, so the force this dislocation exert on the obstacle is magnified by their number. So the obstacle can be overcome. Obstacle can be overcome when? Let me just erase this part. Obstacle can be overcome when? Can you imagine when the obstacle can be overcome? Well, obstacle can be overcome at the time when N tau minus tau 0 multiplied by B must be greater than equal to F star. Then only the obstacle can be overcome. Remember, this is tau. So we can write down N sigma minus sigma 0 by 2 multiplied by B, that is equal to when reaches a critical, more than a critical value, then only the obstacle can be, this obstacle can be overcome. Then only it can be overcome, right. So you understood, right. First is that we connected what? Connected the dislocation density in the grain or number of dislocations with this shear stress. So what did he say? If number of dislocations is n and each dislocation is having displacement given by the vector B, and then n multiplied B is total displacement. That once you multiply with the shear modulus, that gives you the force per unit length, correct, on the dislocation, on this plane for this dislocation pile up. And that can be written as C multiplied by sigma minus sigma 0 multiplied by D divided by E by B, where D is the grain size, sigma is this tensile compressive stress, E is the elastic modulus, and B is the Berger vector, and C is a constant. And I told you what is C, so you can figure out from this equation also. So therefore, the obstacle which is there in the form of grain boundary can be overcome only when this equation is satisfied. N tau minus tau 0 multiplied B, NB is again, as you know, that is the total displacement multiplied by tau minus tau 0. Tau is the applied shear stress, and tau 0 is the shear stress which is used for other strengthening. So tau minus tau 0 is basically shear stress applied because of dislocation pile up on the grain boundary. Once that reaches more than a critical value F star, then this pile up will lead to start of dislocation motion, generation and the movement in the grain 2, right. That is what is the thing we discussed. So now we can put the value of n is equal to C sigma minus sigma 0 to D by EB multiplied by sigma minus sigma 0 by 2 B, correct. That is what is n is this, and this factor is this sigma sigma by 2, that must be equal to F star, right. So then what we can write down? If you make the equations very clearly, you get sigma minus sigma 0 square, right. So that's sigma minus sigma 0 square, sigma minus sigma 0 square becomes what? Square becomes 2 F star multiplied by E, correct, divided by C into B, very clear, C into B into B by D, right. We can write down, as you know, B get cancelled, but we are not cancelling both the B's, we are keeping both the B's. So we can sigma minus sigma 0, sigma minus sigma 0, these two become square, okay, and this will be 4, 2 into 2 become 4, and F star is remaining F star, okay, and remember this is the limit, that is why you put the equality sign. So that's, we can take it down to the other slide. So okay, so let me write down, so sigma minus sigma 0, that's equal to twice F star, and this is square actually, F star 4 F star multiplied by F star E multiplied by C B into B by D, correct. That's what you can write down. This is what it's, you get it, okay. You do, if you do the mathematics properly here, correct. So I think you should try and do it as much as possible. So what does you do? You get sigma minus sigma 0 is equal to 2 F star E multiplied by C into B to the power half into B D to the power half, correct. So that we can write down sigma minus sigma 0 is equal to K constant divided into B by D to the power half, where K is a constant which is given by this. Remember, this constant depends on the critical or the obstacle strength multiplied by elastic modulus divided by B, C into B, okay. So that's basically depends on a particular material. Obviously, grain boundary for a particular material will dictate the F star and E also. Berger vector is given by crystalline structure, and C, we have seen what is C. C is a constant which depends on many factors, right, that we have discussed. C can be easily obtained from this. If you see that C is equal to, C is what? 4 1 minus mu pi divided by 3, correct. That is what it is. That is really purely constant in a material, because nu is a constant. In for most of metal is 0.33 and pi is a constant, therefore it is a constant. So then we can write down sigma is equal to sigma 0 micro by K B by D to the power half, correct. So, many cases people write sigma is equal to constant K, this is what it is, and that is the Hall-Petch equation, or you can write then sigma 0 K T to the power minus half, that is the Hall-Petch equation. Which you have derived and you should do yourself, correct? You must do yourself. That is the Hall-Petch equation. So, you understood how to derive the Hall-Petch equation, right? Very well. So, now the question is this, the quantity K star or K dot here basically is the dimensions of stress, as you can clearly see. It is the characterizes the strength of the obstacle or the boundary. Value normally typically ranges K star, value ranges from 5 to 15 gigapascal. That is what it is. It is about equal to the ideal strength. There is very important that as the grain size decreases, the strength increases. That is what it tells you. So, that means what? As we go down to the nanocrystalline grain, the strength will increase drastically. That is why we can come back to the nano size. So, as you know, D is basically 1/2 minus. So, therefore, effect is more significant. This is not a linear. Effect is more significant because of the factor half, and this is inversely proportional. But you know, this can happen very easily till a critical grain size, below which no longer this is possible. We will come back and discuss about that aspect also. So, first of all, you understood that if you plot grain size, hardness versus grain size here for nanocrystalline copper, you can see here its strength significantly increases. You look at the value of hardness at 100 nanometers, that is about 400 MPa, and look at the value of hardness at 10 or maybe 5 nanometers, that is almost 2500 MPa, that is a 2.5 GPa, right, and 1 GPa is 1000 MPa, right. So, therefore, very clear that as you decrease the grain size, the strength increases rapidly, very, very rapidly, and it has increased 4 order of magnitudes here. That is the advantage of making nanocrystalline grains. You can make the material strong and strong and strong, but is it possible to make the material strong and strong and strong by decreasing the grain size from micrometer to about 2 nanometers? Answer is no, because as you clearly see here, this is nanocrystalline copper. You see here the strength increases drastically, then strength remains constant. In fact, it can decreases also. There are many materials it has been found the strength decreases. So, that means the Hall-Petch equation breaks down below a grain size. You must be thinking, why does it happen? That is not very difficult to understand. Let me first show you all these slides, then I will come back to it. Okay, we will come back to it. There are a few more things to show. This is nickel electrodeposited, and as you can clearly see, the grain size still about 2000 nanometers, does not change much, but then something about 100 nanometers, so grain size shoots up from 2 GPa to hardness to about 8 GPa. That is about 4 times increase of hardness, correct? And this can be also plotted as function of d to the power minus half. You have to see whether the Hall-Petch equation is valid or not. And it is found the Hall-Petch equation is really valid till a value of d to the power minus half of 0.3, below which or above which, actually not below which, the Hall-Petch equation breaks down. So, Hall-Petch equation has been observed in case of nanocrystalline copper breaking down below a certain grain size. Similarly, it has been observed in case of nickel also, it is breaking down for below a certain grain size. Not only that, even if you create copper nickel multi-layers means what? You can deposit thin films layers, copper, then nickel, like this, okay? Copper, nickel, So this is copper, nickel, copper, nickel, copper, nickel, copper, nickel. Okay. So this is nickel actually. So if you deposit this kind of multi-layers, and if their bilayer periods vary, bilayer period means what? Okay. Bilayer period means this to this distance. This is D. Half center of this copper to the center of this copper. In between there is a nickel layer. So that's the bilayer period. If this bilayer period is plotted as a tensile strength is plotted as a function of bilayer period, you can clearly see that there also this equation shows a tremendous increase of strength. But it has been observed this equation breaks down below a certain value of bilayer period. So this is universal. Nanocrystalline copper, nanocrystalline nickel, bilayer copper nickel, and many other materials this equation has been found to break down. So the question is that then why does it break down? Why does it so easy to so much happens, so such a thing happens at all in nanocrystalline material? That's very important. So you can see the mother nature, right? Initially we thought when you derive the Hall-Petch equation here, we thought that let us keep on decrease the grain size. You will have tremendously strong material. Unfortunately, that doesn't happen. There is a limit to which the strength increases, and then if you still decrease the grain size, strength decreases. And this is known as the grain boundaries softening. Okay, remember this word. Mostly the Hall-Petch equation is derived because of the grain boundary strengthening. Grain boundary is acting as an obstacle for the motion of dislocations, and that's why they provide the strengthening. Now the question is here, below a critical grain size, instead of having strengthening, you have a decrease of the strength, or rather grain boundaries act as a decrease of strength. Because as you know, smaller the grain size, more is the grain boundary area. So more is the grain boundary area, more should be the strength, but we are seeing opposite. We are seeing the strength going down. That's why it is called grain boundary softening. Softening means material is becoming softer and softer as the grain size decreases. Now the question is, why does it happen? Let us set some light onto it, and then we will stop this lecture. Well, that's very easy to understand. The grain boundary strengthening is because of the pile up of dislocations at the grain boundaries. So this pile up of dislocation means you need many dislocations to be accommodated inside the grain. Then only the pile up is possible, right? If you have two passengers standing in front of a railway counter to buy a ticket, there is no pile up. Only when you have tens of passengers or hundreds of passengers, then you have pile up. But think about it. If you want to create tens of passengers in front of a ticket counter, you need space. You need critical space. They cannot, stand, just as close as possible, so that they can touch each other, they can force each other. This will be uncomfortable situation, right? So they will be standing, the passengers will be standing in front of the railway passage counter, ticket counter, in a safe distance, so that they don't touch each other, they don't force on each other, they are comfortable, right? Same thing is valid for dislocations. When dislocations are lining up inside a grain, they must be sitting at a distance from each other, which will make them comfortable. Otherwise, the stress field associated to each dislocation will interact, will fall on each other. And because of this stress field falling on each other, they will be uncomfortable. They will feel jittery. Just like if you ask the human standing in the queue to come and, just stand just right behind each other, they will not feel each other good actually. They will feel that they are crushing onto each other. That's not good. Same thing is true for dislocations. So now if you keep on decrease the grain size, what is happening? The length on which this dislocation can stand is decreasing. That's what it is. So you have a big grain size and you have a small grain size. This length L on which dislocation can stand, L and L1. So L1 is smaller than L, right? And you can have big grain, this is say this L, and this is again smaller than this L, right? So what do you see? As the gain side decreases, the length on which dislocation can pile up is decreasing. So there will be critical length where only 2 dislocations can pile up. And when 2 persons are standing in front of a ticket counter, they can peacefully sit far apart from each other without applying force on each other. There will be no pile up, there will be no stress acting on the gain boundaries. If no stress is acting on the gain boundaries action as an obstacle doesn't make any sense, okay? Because amount of stress applied on the gain boundaries will be much small. Even you can have gain side which is much smaller, where you can only have 1 dislocation. There, this dislocation is comfortably sitting inside the grain without even interacting with other dislocations. So therefore, there will be no force acting on the gain boundaries. So now you understand, right? That is what is happening as you decrease the gain size. As you keep on decreasing the gain size, this is exactly what is happening. Dislocations, the number of dislocations inside the grain is decreasing till it reaches 1 or 2 in the grain. Once it reaches that value of the gain size, when only 1 or 2 dislocations can be accommodated inside the grain, Hall-Petch equation loses its meaning, because then the concept of pile up and concept of this stress acting on the gain boundary is no longer happening. That particular aspect of the strengthening because of gain boundary is no longer valid. So that's why Hall-Petch equation breaks down below a certain grain size. Remember these aspects. This is a very critical thing which you should understand. The breaking down of Hall-Petch relationship is also same thing. The same thing is true for bilayers. If you decrease the bilayer thickness, the length on a dislocation pile up can happen also decreasing. So I would rather say that these aspects of pile up and the force acting on the obstacle is only can happen when you have a critical size of grain, and that size is what is where this kind of breakup or this kind of breakdown of Hall-Petch relationships or equation can happen. Okay, you can see here it is happening here, say it is happening there also, it is happening here also. So everywhere it is happening, correct? So what did I discuss in this today's lecture? Let us kind of compile. So I told you that tensile test is the most important test to determine the mechanical behavior of material, correct? Then I talked about multi-grain materials, how defects can pile up at the gain boundaries and gain boundary can act as an obstacle, correct? Then I derived this Hall-Petch equation, and finally I showed you why the equation breaks down. So that's for today. We'll come back in the next lecture and discuss some more aspect of mechanical behavior and move on to the other aspects. Thank you.